Hi friends, welcome to the lecture of number theory. In last lecture we have completed what is an fundamental theorem of arithmetic and what is its use. Okay, that is fundamental theorem of arithmetic is also used to find out the GCD of any given number of integers, and we have seen some results depending on that theorem. In last lecture we have already seen root 2 is not a rational number, but there is one alternative proof for this one. Let us see what is with the first one. After that we will the second proof of this statement, that is root 2 is not a rational number. In first method we have proved that root 2 is not a rational number by using this method, that is we have assumed the contradiction that root 2 is a rational number. That is, if root 2 is a rational number, then it can be expressed in the form of p by q, where q is not equal to 0. That is a by b whenever b is not equal to 0, and GCD of these two integers a and b is 1. After that we have squaring on both sides, we get 2 is nothing but a square upon b square, and from that a square is nothing but 2 times b square. 2 times b square can be written as 2b into b. As a square is a multiple of this b, then b must divide a square, that is b divides a square. Now there are two possibilities for b, either b is a prime or composite. For that let us consider b is greater than 1. As b is greater than 1, then by the fundamental theorem of arithmetic.
Sir, your voice is low.
Okay. So there are two possibilities for b, that is b is either a prime number or it is a composite integer. Now let us consider b is greater than 1. Then by the fundamental theorem of arithmetic, there exists some prime p which divides this b, since any integer which is greater than 1 can be expressed as a product of prime uniquely. This one is the statement of fundamental theorem of arithmetic, and from that one there exists one prime p such that p divides b. Okay, that is, if b is a prime, then there exists some prime divisor for this b. Okay, now as here b divides a square and here we get p divides b, then by the transitive property p divides b and b divides a square, which implies p must divides this a square. Okay, as p divides a square, then p, that is p divides a into a. And in previous lecture, that is last one lecture, we have already proved that if p divides ab, then p either divides a or p divides b. Then from this one, as a and b are same, then p divides a, which implies here we get p divides a and p divides b, and p divides b, that is p is the common divisor of a and b, and GCD is nothing but the greatest common divisor of ab. If p is the greatest one, then GCD of ab will be equal to p, but here we don't know whether this p is the greatest divisor or not. Therefore from this we conclude p must be greater equal by p, since p is the common divisor of both a and b. Now okay, now but root 2 is nothing but a upon b, that is root 2 is as root 2 is a rational number, then it can be expressed in the form of a by b, where b is not equal to 0, where GCD of ab will be equal to 1. But here we get GCD of ab is greater equal by b, greater equal by p, but p is a prime number. As p is a prime number, then p must be greater than 1, but already we know that GCD of ab is equal to 1. But here we get GCD of ab is greater equal by p. So this one is the contradiction to our GCD of ab will be equal to 1, and this contradiction arises due to our wrong assumption. Which one is that is the assumption root 2 is a rational number. Hence that is, as here we have considered b is greater than 1. As b greater than 1, then we get a contradiction to GCD of ab will be equal to 1. Therefore there is only one possibility for b, which is a equal to 1. Okay, if possible, if suppose b is less than 1, then b is less than 1, then also we get, then also from the fundamental theorem of arithmetic we get GCD of ab is greater equal by p. Therefore therefore b is not greater than 1 nor less than 1, therefore b must be equal to 1. If suppose b is less than 1, if b less than 1, then again by the fundamental theorem of arithmetic, again we get one prime divisor for this b, and from this we get p, and which is contradiction to GCD of ab will be equal to 1. Therefore neither b greater than 1 nor less than 1, therefore b must be equal to 1. Therefore a square equal to 2b square becomes a square is equal to 2 into 1, and which is a square equal to 2. But this one is not possible because there does not exist any integer which can be multiplied to itself, it gives a number 2, since such a number is not possible in the set of integers. integer. Therefore, this one is a contradiction to our assumption that root 2 is a rational number. Hence, our assumption is wrong. As assumption is wrong, rational number. Now, there is one more method to assumption that root 2 is a rational number. As root 2 is a rational number, then it can be expressed as a form of a by b whenever b is not equal to 0 and GCD of ab will be equal to 1. Root 2 equal to ab, then a is nothing but root 2 b. As here GCD of ab equal to 1. Again, by the property of GCD, there exists some integers r and such, yes, such that GCD 1 can be expressed in the linear combination of a and b. That is ar plus bs is nothing but root 2 ar plus root 2 bs is equal to root 2. But a is nothing but a is equal to root 2b. Root 2b into root 2, which is 2 times br, plus again b is nothing but a by root 2. From this one, b is nothing but a by root 2. If we put the value of b as a by root 2 in this one, then root 2 gets cancelled and we get as, that is 2br plus as is equal to. Similarly, a and s both are integers. Then the linear combination of these 4 integers must be an integer. Therefore, from this one here, root 2 must be an integer. Okay, this representation of root 2 needs us to conclude that root 2 is an integer, but root 2 is not an integer. As root 2 is not an integer, therefore, which is a contradiction to our assumption that root 2 is a rational number. Hence, root 2 is not a rational number. Therefore, by using this method also, we can prove that root 2 is not a rational number. Now, we have to see the next result, which is the product of 2 or more integers of the form 4n plus 1 is again in the same form. Therefore, here we have to show that if we take any number of integers of the form 4n plus 1, then its multiplication is again in the same form. And for that, if we consider any 2 integers of the form 4n plus 1 are again in the same form, then we conclude that any number, if we take any number of integers and take its product, then it is again in the same form, that is 4n plus 1. Let us consider a and b are 2 integers of the form 4n plus 1. That is, a is nothing but 4k plus 1 and b is nothing but 4k dash plus 1. Now we have to take its multiplication, that is a dot 4k plus 1 into 4k dash plus 1. Now, which is nothing but 16k k dash plus 4k into 1 4k plus 1 into 4k dash, which is 4k dash plus 1 into 1 1. Now let us take common 4 from the first 3 terms. Then we get 4 into 4k k dash plus k dash plus this one as it is. That is, this one a into b is nothing but 4n plus 1, where value of n is nothing but 4k k dash plus k dash. That is, as k 4k k dash plus k dash is again an integer. Therefore, the product of 2 integers of the form 4n plus 1, that is a into b, is again in the form 4n plus 1. If we take 3 integers, then first 2 integers are in the form of 4n plus 1 and third one is also in the form of 4n plus 1. Again, its product is again in the same form. Therefore, if we take 2 or more integers of the form 4n plus 1, then its product is again in the same form. Okay, now the next one is, there is an infinite number of primes of the form 4n plus 3. Here we have to prove that there are infinite number of primes of the form 4n plus 3. If possible, let us consider there are only finite number of primes of the form 4q plus 3. Either we take 4q plus 3 or 4n plus 3, where q is an integer. So, as here we have to prove that there are infinite number of primes of the form 4q plus 3. For that, let us consider there are only finite number of primes of the form 4q plus 3, and which are nothing but p1, p2 up to so on pn. That is, there are only n primes of the form 4q plus 3. Okay, now, so p1, p2 up to so on pn are the only primes in the ascending order. Then the remaining primes, if any, then they are of the form 4q plus 1. Since we know that every integer is of the form 4q plus 1, 4q plus or minus 1, 4q plus or minus 2, or 4q plus or minus 3. But 4q plus or minus 2 is an even numbers. Therefore, there is no prime in the form of 4q plus or minus 2. So, all the primes are of the form 4q plus 3 or 4q plus 1. As there are only n primes which are of the form 4q plus 3, then all the remaining primes are in the form of 4q plus 1. Okay. Now let us consider capital N be any integer which is nothing but 4 times the product of these n primes, that is p1 p2 up to so on pn minus 1. That is n is one integer which is 4 times the product of p1 p2 up to so on pn, that is 4 times the product of these n primes minus 1. Therefore this n can be written as 4 times p1 p2 up to so on pn minus 1 plus 3. That is this one is nothing but the previous step, that is 4 times p1 p2 up to so on pn minus 4 plus 3. Minus 4 plus 3 is nothing but minus 1. Okay, now again this one as p1 p2 up to so on pn all are the prime numbers, therefore its multiplication is again in a integer, and integer minus 1 is again an integer. Therefore let us take this, its value will be equal to q, that is p1 p2 up to so on pn minus 1 is nothing but something q. Therefore this capital N is again in the form of 4q plus 3, where q is nothing but p1 p2 up to so on pn minus 1. Okay, now there are two possibilities for this capital N. Either this capital N is a prime number or it is a composite number. If capital N is a prime number, then it is prime greater than Pn. Since capital N is a 4 times the product of these n primes minus 1. Therefore, obviously capital N is greater than Pn. And we have considered already there are only n primes, and which are nothing but P1, P2 up to so on Pn. Therefore, this capital N is must be greater than Pn. Okay, now the second possibility, if n is composite number. If n is composite number, then it must have divisor other than 1 and n. Therefore, it cannot be in the product of primes of the form 4q plus 1. Therefore, if n is composite, then all the factors of this n are not in the form of 4q plus 1. If all the prime factors of this n are in the form of 4q plus 1, then in previous result we have already proved that the product of any, that is the product of 2 or more integers of the form 4n plus 1 is again in the same form. So if we take, if the n has all prime factors are in the form of 4q plus 1, then its multiplication is again in the same form, that is 4q plus 1. But here capital N is nothing but 4q plus 3. Therefore all its prime factors are not in the form of 4q plus 1. Okay, so this n must have at least one prime factor of the form 4q plus 3. There exists one prime factor which is of the form 4q plus 3. But this 4q plus 3 cannot be any one of the prime element in p1, p2 up to so on pn due to equation 1. This 4q plus 3 is not belonging to these n prime numbers. This is because from the equation 1, as this capital N is 4 times the product of these n primes minus 1, therefore its any prime divisor must be greater than all the primes p1, p2 up to so on pn, since n is nothing but 4 times p1, p2 up to so on pn minus 1. So if there is any prime divisor for this n, then it must be greater than this n prime numbers. As here we get one prime factor, therefore it must be greater than pn. So in both the cases, that is either n is a prime number or n is a composite number. Here we get a prime number which is greater than these n primes and which is in the form of 4q plus 3. But this is contradiction to our assumption that there are only n primes in the form of 4q plus 3. Since here we get one prime which is greater than all these n primes and which is in the form of 4q plus 3. So this one is the contradiction to our assumption, that is there are only finite number of primes of the form 4q plus 3. So our assumption will be wrong. As assumption will be wrong, therefore the correct statement is nothing but there are infinitely many primes of the form 4q plus 3. Okay, is anyone have doubt? कोणाला काही डाऊट आहे का? डाऊट आहे की नाही? नेक्स्ट कन्सेप्ट घ्यायचं का मग?
हो सर.
बोला हो, बोलायला काय कळतंय तर ना तुम्हाला, का काही प्रॉब्लेम आहे?
No, sir.
Okay, ठीक है. The next one is Goldback conjecture. This one is the famous unsolved problem concerning to primes. This one is again depending on the prime numbers, and it states that is the Goldback conjecture is that it states that every even integer can be written as a sum of two numbers which are either prime or 1. That is, if you take any even integer, then it can be expressed as a sum of two prime numbers, or one of them is a integer 1. That is, first even integer is nothing but 2, therefore 2 can be expressed as a 1 plus 1. Therefore 2 is nothing but the sum of two integers which are 1 plus 1. Now next even number is nothing but 4. Therefore 4 can be expressed in as a sum of two prime numbers which are nothing but 2 plus 2. 2 is a prime number, or we can express 4 as a sum of two integers which are nothing but 1 and 3, in which 1 is a integer and 3 is a integer which is a prime number. Similarly 6 can be expressed as 3 plus 3, that is a sum of two primes, 3 plus 3. Also we can express 6 as 1 plus 5. Similarly for 8 and 10, that is 3 plus 5 or 1 plus 7, and 10 as 3 plus 7 or 5 plus 5. Therefore this Goldback conjecture states that if we take any even integer, then it can be written as sum of two numbers. The two numbers are either prime or they are integer 1. This is true for all the even integers. Okay. Now there is one method, sieve of Eratosthenes. That is, this method is also useful to find out the number of integers less than some fixed number n. Let us see its working principle. That is, sieve of Eratosthenes. Let n be a given integer. Then we can construct a table of prime not exceeding n by a method is known as sieve of Eratosthenes. That is, if suppose there are n integers, then we can construct a table of prime not exceeding this n by a method, and that method is called as sieve of Eratosthenes. We will explain this method by taking n equal to 100 as follows. And for that we have to first write all the integers from 1 to 100 in their natural order as follows. First let us write all the integers from 1 to 100, that is 1 to 10, 11 to 20, 21 to 30, 31 to 40, and similarly 91 to 100. That is, we have to write first 100 integers, okay, in a table. Now we have to use this above principle. That is, we have to first see what is its working method. Okay. Now we know that 1 is neither a prime number nor a composite number. Therefore here we have to take the first prime number, which is a 2, as 2 is the first integer in the table which is a prime. Now we have to retain 2 and strike out all the integer multiple of 2. That is, we have to retain this 2. That is, we have to keep this 2 as it is, and we have to strike out all the multiples of this 2. That is 4, 6, all the even integers. Okay. Now after that 3 is the next prime number. Okay. Again we have to retain this 3 as it is and strike out all the integer multiple of 3. Now after that the 5 is the next smallest integer which is a prime number. Again we have to retain 5 as it is and strike out all the multiples of 5. After 5, 7 is the next smallest integer which is again a prime number, and we have to retain 7 as it is and strike out all the multiples of 7. But after 7, number 11 is the next prime which is greater than 100. Hence the unstriked numbers in the table are not divisible by any prime less than or equal to root 100. Therefore all the unstriked numbers will be a prime numbers. That is, in this method we have to first write down all the integers from 1 to 100, as 1 is neither a prime nor a composite number. Therefore keep 1 as it is. Now after that we have to take the next prime number which is a 2, and we have to keep this 2 as it is and strike out all the integers which are the multiples of this 2. That is, strike out all the integers which are divisible by this 2. That is, all the even integers. Therefore after that step we get only odd integers remains. There, out of these odd integers we have to take the next prime 3, and we have to keep 3 as it is and strike out all the multiples of 3. And similarly for 5, 7. After 5 and 7, we have to stop this method, since in previous lecture, that is in some one lecture, we have proved that if n is an integer and which is not divisible by any prime less equal by root n, then this n must be a prime number. Therefore there is no need to go for the prime 11. Therefore here we have to keep the primes 2, 3, 5 and 7 as it is and strike out all the multiples of this 2, 3, 5 and 7. Then all the unstriked integers are nothing but the prime numbers. दॅट इज या मेथडमध्ये काय करायचं, तुम्हाला फक्त अगोदर तुम्हाला 1 ते 100 पर्यंतचे सगळे नंबर लिहून काढा. 1 ते 100 पर्यंतचे सगळे नंबर काढल्यानंतर तुम्हाला आपल्याला माहिती आहे की 1 हा प्राइम पण नाहीये, कंपोजिट पण नाहीये, त्यामुळे याला एकाला सोडून द्यायचं. परत मग नेक्स्ट प्राइम कोणता येईल, 2 येईल. 2 ला जसंच्या तसं ठेवून 2 च्या मल्टिपल मधले सगळे एलिमेंट आपल्याला खोडून काढायचे, म्हणजे 2 च्या मल्टिपल मधले कोणताही नंबर हा प्राइम नंबर नसणार आहे. ही मेथड तुम्हाला नंबर ऑफ प्राइम नंबर्स काढण्यासाठी युजफुल आहे. त्याच्यामुळे 2 च्या मल्टिपल मधले सगळे नंबर हे कसे असतील, कंपोजिट नंबर असतील. जर ते कंपोजिट नंबर असतील तर त्या सगळ्यांना काढून टाकावं लागेल, कारण 2 हा त्या सगळ्यांना डिवाइड करतो. म्हणजे याच्या मल्टिपल मधले सगळे नंबर जातील. याच्या मल्टिपल मधले सगळे नंबर कोणते असतील तर ते इव्हन नंबर असतील, म्हणजे तुमचे पूर्ण इव्हन नंबर ऑलरेडी गेलेले आहेत. म्हणजे आता राहिलेले काय आहेत तुमची ऑड इंटिजर्स. नाव वी हॅव टू टेक द नेक्स्ट प्राइम नंबर अँड विच इज नथिंग बट 3. मग नंतर 3 ला जसं तसं ठेवायचं, कारण 2 डज नॉट डिवाइड 3. therefore next prime, as 3 is a prime number, then we have to keep this 3 as it is and strike out all the multiples of 3. that is परत इथं तुम्हाला 3 च्या मल्टिपल मध्ये जितके नंबर असतील ते परत काढून टाकायचे, म्हणजे ते सगळे ऑलरेडी कंपोजिट नंबर आहेत, कारण त्यांना 3 डिवाइड करणार आहे. मग 3 नंतर 4 हा प्राइम नाहीये आणि 4 तुमचा नसणारच आहे, कारण 2 4 ला डिवाइड करतो, याचा अर्थ 4 तुम्ही ऑलरेडी काढून टाकलाय. त्याच्यानंतर कोणता असेल, 5 असेल. आता 5 मध्ये आता असे एलिमेंट शिल्लक आहेत जे 2 आणि 3 ला डिवाइड झालेले नाहीत, म्हणजे ते 5 ने डिवाइड होतील. 5 ने डिवाइड झालेले नंबर जितके असतील तितके काढून टाकायचे, परत जे असतील ते शिल्लक असतील. त्याच्यानंतर 6 नसणारच आहे, कारण 6 ला 2 आणि 3 दोन्ही डिवाइड करणार आहेत, याचा अर्थ तो ऑलरेडी याच्यामध्ये नाहीच आहे. म्हणजे नेक्स्ट प्राइम कोणता असेल, 7 असेल, 7 असेल. 7 च्या मल्टिपल मध्ये जितके नंबर आहेत तितके सगळे काढून टाकायचे आणि बाकीचे असतील ते असतील. आता पुढचे हे 3 नंबर 8, 9 आणखीन 10, हे तिन्ही, या तिन्ही मधला 8 आणखीन 10 हे 2 पासून डिव्हिजिबल आहेत आणि 9 हा 3 पासून डिव्हिजिबल आहे, म्हणजे हे ऑलरेडी नंबर नाहीच आहेत. ओके, हे नंबर ऑलरेडी नाही आहेत. म्हणजे आता तुम्हाला नेक्स्ट प्राइम कोणता असेल, 11 नंबर हा नेक्स्ट प्राइम असेल 7 नंतर. पण एका लेक्चर मध्ये आपण मागे प्रूव्ह केले की n हा कोणता तरी एक इंटिजर आहे आणि तो जर डिव्हिजिबल नसेल कोणत्याही प्राइमनी तर तो इटसेल्फ हा प्राइम नंबर असेल. म्हणजे पुढचे सगळे नंबर जे की कोणत्याही या 10च्या आत मधल्या कोणत्याही प्राइमने जर डिव्हिजिबल नसतील तर ते इटसेल्फ प्राइम नंबर असतील. आणि ते नंबर ऑफ जितके नंबर तुमचे शिल्लक राहिलेले आहेत ते सगळे हे तुमचे प्राइम नंबर असतील. कुणाला काही डाऊट?
नो सर.
नो सर.
कळाली ना मेथड?
हो.
इझी आहे. फक्त 1 सोडून द्यायचा. रूट 100च्या मध्ये जितके प्राइम आहेत त्यांच्यातील सगळे, त्यांच्या मल्टिपल मधील सगळे नंबर काढून टाकायचे आणि उरलेले जितके नंबर असतील ते 100च्या मधले तुमचे नंबर ऑफ प्राइम नंबर्स असतील. ठीक आहे. नाउ नेक्स्ट वन इज द Euclid's theorem and it states that there are infinite number of primes. Okay, in this method, in this theorem we have to prove that there are infinite number of primes. For that we have to assume the contradiction that there are only finite number of primes. Let us consider p1, p2 up to so on pn are the only n primes in ascending order. Let us consider the next prime, let us construct one integer n from these n primes. That is, n is nothing but product of these n primes plus 1. Therefore obviously n is greater than pn, since it is a product of these n primes plus 1. Therefore obviously this capital small n is greater than the nth prime integer. Therefore again there are two possibilities for the n. Either n is a prime number or it is a composite number. If suppose n is a prime, then it shows that there exists a prime greater than pn, since n is greater than pn. If n is a prime, then this one shows that there exists a prime greater than 1, and in this case we get a contradiction to our assumption. There are only finite number of primes. Now the second case is n is a composite number. If n is a composite number, then it is not divisible by any prime among these n primes p1, p2 up to so on pn. As such a division leaves 1 as the remainder. Here, these n primes p1, p2 up to so on pn does not divide this n. If they divide, then we get a remainder 1. As remainder is 1, then we say that this capital small n is not divisible by p1, p2 up to so on pn. So small n is not divisible by these n primes p1, p2 up to so on pn. As this is not divisible by these n primes, and as it is a composite number, then it must have at least one divisor other than 1 and n, and which is a prime. That is the smallest divisor of any integer is a prime. As n is a composite number, therefore it is an integer. As n is a composite, it must be an integer. Therefore, according to that segment, its smallest divisor must be a prime number. But p1, p2 up to so on pn are not the divisors of n. Therefore, here exists one prime other than this n primes, which divides n, and this prime number must be greater than this n prime numbers, since the first n prime numbers are nothing but p1, p2 up to so on pn. But here we get one prime divisor other than this p1, p2 up to so on pn, then it must be greater than this n primes. Okay, now than pn. Thus, in both the cases, therefore, in this case also we get one prime greater than pn. Therefore, either n is a prime number or n is a composite number. In both the cases, we get a prime greater than pn. But this one is a contradiction to our assumption that there are only finite number of primes, since here we get one more prime other than this n primes. Therefore, our assumption will be wrong. As our assumption will be wrong, then the correct statement will be nothing but there are infinitely many number of primes. Okay, there is one alternative method to solve this one. Let us assume the contradiction that there are finite number of primes p1, p2 up to so on pn in ascending order, and pn is the last prime. Let us consider one integer n which is equal to p1, p2 up to so on pn plus 1. Then obviously n is greater than 1. Now we have to use the fundamental theorem of arithmetic for this n, since n is greater than 1. Then by the fundamental of theorem of arithmetic, n is divisible by some prime p. But there are only n primes. As there are only n primes, then this prime p must be belonging to this p1, p2 up to so on pn, since there are only n primes. Therefore, as p is a prime which belongs to these n primes, then p must divide p1, p2 up to so on pn. And by fundamental theorem of arithmetic, we get already a prime divisor for n, that is p divides n. As p divides product of these n primes and p divides n, then p must divide its any linear combination, that is p divides n minus p1, p2 up to so on pn. But n is nothing but p1, p2 up to so on pn minus 1. Therefore, we get p1, p2 up to so on pn minus p1, p2 up to so on pn get cancelled, and 1 as it is. So here we get p divides 1. As we know that p is a prime number and p divides 1. This one is not possible, since the only positive divisor for the integer 1 is 1 itself. As p must be equal, therefore p must be equal to 1, but p is not equal to 1. Since p is a prime number, as p is a prime number, then it must be greater than 1. So here we get a contradiction to p is a prime number, as this one is not true. So our assumption will be wrong, that is there are only finite number of prime numbers will be wrong. Therefore, the correct one will be there are infinitely many number of primes. Okay, now we have to see what are the Euclidean numbers. Okay, let us see. The numbers of the form p hash plus 1 are called Euclidean number, where p hash is the product of all primes which are less than or equal to prime p. That is, what are the Euclidean numbers? The Euclidean numbers are denoted by p hash plus 1, and they are called Euclidean number, where p hash is nothing but the product of all primes which are less than or equal to prime p. If suppose p is equal to 2, then p hash plus 1 is nothing but the product of all primes which are less than or equal to prime p. And here, as p is equal to 2, then p hash plus 1 is nothing but the product of all primes which are less than or equal to 2 plus 1. But there is only one prime which is less equal by 2, and which is 2 itself. Therefore, it is nothing but 2 plus 1, and which is equal to 3. Therefore, this 3 is nothing but the Euclidean number. Similarly, for p equal to 3, p hash plus 1. Now again we have to take all the primes less equal by 2, that is product of all the primes less equal by these 3, and there are 2 primes less equal by 3, which are 2 and 3. Therefore p hash is nothing but 2 into 3 and plus 1 as it is. 2 into 3 6, 6 plus 1 7, therefore 7 is a Euclidean number. Same for p equal to 5, there are 3 primes less equal by 5, which are nothing but 2 3 and 5. Therefore p hash is nothing but 2 into 3 into 5 plus 1, which is equal to 31, and 31 is the Euclidean number. Now here 3 7 and 31 are the prime numbers. Now from this one we have to check whether Euclidean number is always a prime number or not. Up to prime number 13 we get the prime numbers, but if we take p equal to 17, then 17 hash plus 1 is equal to 510 511, and this one is a composite number. As this one is composite number, therefore this one is not a prime number. Therefore there is one note: all the numbers of the form p hash plus 1 need not be prime. Since here we get one number 17 hash plus 1, that is Euclidean number 510 511, which is not a prime number. Therefore all the numbers of the form p hash plus 1 are not the prime numbers. Okay, now we have to see what is an perfect number. Positive integer n is said to be a perfect number if n can be written as the sum of all its positive divisors excluding n itself. So any positive integer n is said to be a perfect number if it can be written as a sum of all its positive divisors excluding that element n itself. That is, here 6 can be written as its positive divisors are nothing but 1 2 3 and 6, but here we have to exclude n. Therefore 6 is nothing but 1 plus 2 plus 3, 3 plus 2 5, 5 plus 1 6, as 6 is equal to 6, therefore 6 is nothing but the perfect number. If we take 4 can be written as 3 plus 1 or 3 plus 1 or 2 plus 2, but 2 it's the positive divisors of 4 are nothing but 1 2 and 4. Now if we exclude the element 4 itself, therefore 1 plus 2 is equal to 3, which is not equal to 4. Therefore 4 is not a perfect number. But in case of 6, if we exclude the element 6 itself and take its sum of its only positive divisors, that is 1 plus 2 plus 3, then it is equal to 6. Therefore 6 is a perfect number, but 4 is not an perfect number. Similarly for 28, its positive divisors are 1 2 4 7 14 and 28, and from the definition of perfect number we have to exclude the element 28 itself, and 1 plus 2 plus 4 plus 7 plus 14, which is equal to 14 plus 7 21, 21 plus 4 25, 25 plus 2 27, and 27 plus 8 will be equal to 28. Therefore LHS will be equal to RHS, and again by the definition of perfect number, 28 is a perfect number. Similarly 496 is again a perfect number, and which is nothing but 1 plus 2 plus 4 plus 8 plus 16 plus 31 plus 62 plus 124 plus 248. Here we have excluded the positive divisor 496, and its sum is nothing but 496. Therefore 496 is an perfect number. Now there is one result, that is if Pn is the nth prime, that is this Pn denotes the nth prime number, then we have to show that Pn is less equal by 2 to the power 2 raised to n minus 1. If Pn is the nth prime, then Pn is less equal by 2 to the power 2 raised to n minus 1. We will prove this theorem by using the mathematical induction on the positive integer n. Let us consider for n equal to 1. If suppose n equal to 1, that is Pn, which is equal to P1. P1 is less equal by 2 to the power 2 raised to n minus 1, but here n is 1. Therefore P1 is less equal by 2 to the power 2 raised to 1 minus 1 0. 2 raised to 0 is 1, and 2 raised to 1 is 2. Therefore P1 is less equal by 2, and according to definition of prime number, the first prime number will be 2. Therefore 2 is less equal by 2. Therefore the result will be true for the first integer, that is n equal to 1. Now let us consider the result will be hold for all the integers which are less equal by n minus 1, and we know that the nth prime Pn is less equal by product of previous n minus 1 primes plus 1, that is Pn is less equal by P1 into P2 into up to 1 Pn minus 1 plus 1. Let us consider, let us take one example, that is let us take the third prime, that is third prime is nothing but 5. and from this one we have to show that 5 is less equal by the product of two primes, product of first two primes plus 1. First two primes are 2 and 3. Product of 2 into 3 will be equal to 6. 6 plus 1, 7. Therefore, 5 will be less equal by 7, and which is true for all the integers. Therefore, Pn is less equal by P1 into P2 into up to so on Pn minus 1 plus 1. That is, Pn is always less equal by the product of its previous n minus 1 primes plus 1. But in previous steps, we have proved that P1 will be less equal by 2. Therefore, P1 will be less equal by 2. P2 is less equal by 2 square. P3 is less equal by 2 to the power 2 square, and up to so on. Pn minus 1 is less equal by 2 to the power 2 raised to n minus 2. Since the result will be true for n equal to n minus 1. Therefore, Pn is less equal by 2 into 2 square into 2 to the power 2 square up to so on 2 to the power 2 raised to n minus 2 plus 1. Now this one is in the form of 2 raised to m plus 2 raised to m into 2 raised to n into 2 raised to p into 2 raised to q, and we know that 2 raised to m into 2 raised to n is nothing but 2 raised to m plus n. Therefore, which is less equal by 2 to the power, we have to take the sum of all the powers of 2, that is 1 plus 2 square plus 2 cube plus up to so on 2 raised to n minus 2 plus 1. Now we have to use here the geometric series. The geometric series of a plus ar square plus ar cube plus up to so on is nothing but a into r to the power n minus 1 divided by r minus 1. That is a geometric series for finite number is nothing but a plus ar square plus ar cube plus up to so on a to the power r raised to n is nothing but a into r to the power n minus 1 divided by r minus 1, where a is nothing but the first integer and r is nothing but the common difference. So here, the first integer is nothing but 1 and r, the common difference will be 2. Therefore, the common difference will be 2. Therefore, 2 to the power n minus 1 divided by r minus 1. R is 2. 2 minus 1 is 1. Therefore, which is nothing but 2 to the power n minus 1 minus 1 divided by 1, which is nothing but 2 to the power 2 to the power n minus 1 minus of 1. Therefore, next step we get 2 to the power 2 raised to n minus 1 minus 1 plus 1. Therefore, Pn is less equal by 2 to the power 2 raised to n minus 1 minus of 1 plus 1. Now, 1 is less equal by 2 to the power 2 raised to n minus 1 minus 1 for all integers n. Let us take for integer n equal to 1. If n equal to 1, then 2 to the power 1 is n equal to 1, then n minus 1 minus 1 will be 0. 2 raised to 0 is 1. 1 minus 1 is again 0. Therefore, 2 to the power 0 is 1. Therefore, 1 is less equal by 1, and which is true for all the integers n. Therefore, as 1 is less equal by 2 to the power 2 raised to n minus 1 minus 1, therefore replace this 1 as 2 to the power 2 raised to n minus 1 minus 1. Since already the LHS will be less equal by this term and 1 is less equal by this one, therefore LHS will be less equal by 2 times this integer. That is, Pn is less equal by 2 to the power 2 raised to n minus 1 minus 1. And as 1 is less equal by this one, therefore replace this 1 as this one. Therefore, which is plus 2 to the power 2 raised to n minus 1 minus 1. Now, as this one is a plus a, which is nothing but 2 times a. Therefore, 2 times 2 to the power 2 raised to n minus 1 minus 1. And which is nothing but 2 to the power 1 plus 2 to the power m plus into 2 to the power n, which is nothing but 2 to the power m plus n, and which is nothing but 2 to the power 1 plus 2 raised to n minus 1 minus 1 plus 1 minus 1 gets cancelled. Therefore, 2 raised to n minus 1 remains as it is. Therefore, Pn is less equal by 2 to the power 2 raised to n minus 1. And from this one, the result will be true for the integer n. Therefore, by the principle of mathematical induction, as the result holds for all the integers n, therefore the result holds for any integer n. Okay. Now, from this theorem, there is one corollary. For any integer n greater than 1, there are at least n plus 1 primes which are less than 2 to the power 2 raised to n. In this theorem, we have proved that if Pn is the nth prime, then Pn is less equal by 2 to the power 2 raised to n minus 1, where Pn is the nth prime. Therefore, as Pn is less equal by this 2 to the power 2 raised to n minus 1, then all its previous n minus 1 primes are also less equal by 2 to the power 2 raised to n minus 1. Okay. Now, from the above theorem, we have that there are primes p1, p2 up to so on pn minus pn plus 1, which are less than 2 to the power 2 raised to n. Here we have taken n plus 1 primes. If we take n plus 1 primes, then we have to just put here n equal to n plus 1. Therefore, pn plus 1 is less equal by 2 to the power 2 raised to n plus 1 minus 1. Plus 1 minus 1 get cancelled, which is less equal by 2 to the power 2 raised to n. Therefore, pn plus 1th prime is less equal by 2 raised to n. Therefore, as n plus 1th prime is less equal by this term, therefore previous its n minus n primes are also less than this term. Therefore, here we get there are at least n plus 1 primes which are less than 2 to the power 2 raised to n. Okay, now if p and q are twin primes, then we have to show that p into q plus 1 is a perfect square. And what are the twin primes? Two primes p and q are said to be twin primes if p and this q equal to p plus 2, which is again a prime, that is p and p plus 2. If both p and p plus 2 are prime numbers, then these two prime numbers are said to be twin prime numbers. As here given that p and q are twin primes, then here we have to show that p into q plus 1 is a perfect square, that is it is a square of some integer. Okay, let us consider, given that p and q are twin primes, as p and q are twin primes, then this value of q is nothing but p plus 2, and which is a prime number. Now let us consider pq plus 1. Pq plus 1, which is nothing but p into q. Q is nothing but p plus 2. P plus 2 plus 1, which is nothing but p square plus 2p plus 1. P square plus 2p plus 1 is nothing but p plus 1 bracket square. Therefore, pq plus 1 is a perfect square. That is, it is a square of integer p plus 1. Therefore, if any two integers p and q are twin primes, then pq plus 1 is a perfect square. Okay. Now, the next result is prove that every odd number which is greater or equal by 9 can be expressed as a sum of 3 odd primes. Here we have to prove that if we take any odd number which is greater or equal by an integer 9, then it can be expressed as a sum of 3 odd primes. Let us see its proof. We see that the smallest number, which is the sum of 3 odd numbers which are prime, that is, here we have to take the odd primes, which is nothing but 3 plus 3 plus 3. Since first odd prime is 3, and the number which is formed by the sum of 3 odd primes will be equal to 9, and this one is the smallest such a number. Now let n be any given odd integer greater than or equal to integer 9, that is, n is greater or equal by 9. Now p1 be an odd prime such that p1 is less equal by n, p1 is less than n minus 4. That is, let us consider p1 be an odd prime which is less than n minus 4. As given that n be an odd integer, similarly p1 is also an odd prime, therefore n minus p1 is an even number. Since odd minus odd will be equal to even, and as p1 is less than n minus 4, if we then from this n minus p1 is greater than 4, since p1 is less than n minus 4. Now by the Goldback conjecture, it can be Goldback conjecture says that if we take any even integer, then it can be expressed or it can be written as a sum of prime numbers, as n minus p1 is a prime number. Since n and p1 both are odd integers, therefore its subtraction must be an even integer. As it is even integer, then by Goldback conjecture it can be written as a sum of two primes p2 and p3, that is, n minus p1 is nothing but p2 plus p3. If we add p1 on both sides, then n is nothing but p1 plus p2 plus p3. Therefore, given any odd integer, n can be expressed as a sum of the odd primes, as p1, p2, p3 are all the 3 primes. Therefore, it is true for all the integer n which is greater or equal by 9. Since here we have already considered this n is greater or equal by 9. Therefore, from this one, we conclude that if we take any odd integer or any odd number greater or equal by 9, then it can be expressed as a sum of 3 odd primes. Okay.